Hello, good morning student. Today we are going to start or we are going to discuss the remaining point of the disubstituted cyclohexane. We are talking about or discussing about the chapter number 2, stereochemistry of disubstituted cyclohexane. So in the previous lecture I already I already taught you about the 1,2 disubstituted cyclohexane, that is the and with the following point we have discussed that one. First point, geometrical isomerism. Second one is optical isomerism. Third one is a conformational isomerism, and fourth one is a relative stability, right? So in that way we are going to learn this whole chapter with respect to this point. Now in this chapter, in this lecture we are going to talk about relative stability, that is a CH-2 AE form. For example, CH-2 dimethyl cyclohexane. As we know that this is a structure number first, which is CH-2 dimethyl cyclohexane. Why it is a cis? Because both the methyl group are on the same side of the general plane, and that's why it is called as a cis. And 1,2, why 1,2? Because both the methyl group, two methyl group are the substituent, they are present at 1 and 2 position, therefore it is a 2. Methyl, dimethyl means 2 methyl groups are there, and that is a cyclohexane. Now flipping, as we know that flipping is a process where one of the chair conformation converted into as another chair conformation, and during that process what is happening, do you remember during that process, during flipping process, axial bond becomes as a equatorial and equatorial bond becomes as a axial one. That's it. Now look at here, this is a carbon number 1, 2, now here is a 3, 4, 5 and 6. After the flipping, one carbon atom here is above the plane, now it becomes as a below the plane, and this axial bond, now this axial bond going to convert into as a equatorial one. But that position, if you put a hand here, it is above the plane, here also it is above the plane. Now look at as a carbon number 2, where the methyl group which is present at equatorial position, right? Now what is going to happen after the flipping, that is going to present at axial position. Look at, this is a axial position. Now this one, now you can call it as, this is a structure number 2. Now you put the mirror here, this dotted line, nothing but imagine it is a mirror. Now this is a mirror, and what do you see in the mirror? Their mirror images. How does it looks? It looks like this one. This will look like this one, right? Okay, then this axial one, this one. Now at 2 position, this methyl group will be here, CH3, equatorial position, axial position, and as we know that here is a flipping process. Here you can call it as, this is the third one. After the flipping is a process, one chair conformation converted into as another chair conformation, and you are going to get, this is above the 1, 2, 3, 4, 5 and 6. Now this one goes below the plane and the structure becomes as a like this. So here at one position that becomes as a this is a carbon number 1, this is a 2, 3, 4, 5 and 6. Now this carbon number 1, there is a axial position that becomes as a equatorial, and we know that equatorial position of that group here. Now this one, this is equatorial. After flipping we are going to get, this is a axial position, right? Look at there is a axial position, and you can call this is a structure number 4. Yes, in a previous lecture in yesterday's lecture we have talk about geometrical isomerism. 1,2 disubstituted cyclohexane, does it exist? Does it show geometrical isomerism? Yes, it shows as a geometrical isomerism. It shows as a cis and trans. Cis means what? In case of the cyclohexane, if both the methyl group or both the substituents are coming on the same side of the general plane, that is called as a cis isomer. Whereas a trans isomer means what? One of the substituent present above the plane and another below the plane, that is termed as a trans isomer. Remember here both the methyl group are coming on the same side of the general plane, and therefore these structures are cis isomer. Right? Next one we have talked about the optical isomer. Optical isomer means what? If these conformation has no plane of symmetry. These four structures have no symmetry, and therefore it expected to be optically inactive. But these structures are optically inactive. And how do you explain why they are optically inactive? Why they are optically inactive? When one flip into as a 2, which is similar to the third one, or when third flip into as a 4, which is similar to as a first one, means they become as a racemic mixture. Here remember, they are the racemic mixture, and therefore they are optically inactive in nature, right? Optically inactive in nature. Now remember, second thing, conformational isomerism. First and third, they are mirror images of each other, non-super mirror images of each other. That type of the conformer is called as a enantiomer, and 2 and 3 also as a enantiomers of each other, and therefore they are the conformation. Now is the last point is the relative stability. How to calculate, how to determine, or how to measure the relative stability of those conformation. If you look at all these structures are identical or their reactivity is same, we can call at least in this as far as a cis-1,2 dimethyl cyclohexane is considered, all the four structures are identical. They shows as a same stability. Now why they shows as the same stability? And as we know that in general, as the internal energy increases, the stability of the organic compound goes on decreasing. This is a general guideline. Remember, as far as the organic point of view is concerned, what I said just now, those organic compound having as a higher in energy, internal energy are higher, they are the less stable. So that is the general. And now how to calculate as a how to calculate the relative stability or the energy. Now as we know that in a SY BSc you might have learned there is a N-butane Gauche interaction or torsional strain or dihedral angles, and depending upon that we can easily calculate the internal energy. Now here is a look at here how to. Now before that let me show you the model first here. This is a cyclohexane. Cyclohexane, as we know that this is a structure of cyclohexane which is present in most stable conformation. Now here this is a chair conformation of the cyclohexane. What I am going to do now here, I am going to replace this group. This is one of the group which is axial. You can see clearly here one methyl group I am putting at axial position. Now I have second methyl group which is present at equatorial position, but the position should be at equatorial position. Now look at here, I am putting this group at a equatorial position. Now here at a equatorial position, look at carefully. What do you see here? You can clearly see the model here. The models are, this model is a very flexible. So this is a axial position, and one of the another methyl group you consider here, which is at equatorial position here. But that, by looking as a model, this both this methyl group and this methyl group, they are above the plane. If you put as a plane here, these 4 bonds are in the same plane, and both the methyl group are coming on the same side of the carbon-carbon double bond, and that's why it is a cis. Now how do you calculate the energy of this conformation? All are the identical now here. Now there is a what we can call it as a relative stability. Look at here carefully. So 1,3 diaxial interaction, or if you remember your SY BSC's day, there is a N-butane Gauche interaction. N-butane Gauche interaction which has the energy associated with N-butane Gauche interaction is equal to 0.9 kilocalorie per mole. This much amount of the energy associated with the N-butane Gauche interaction that you already learned in your previous class. Now 0.9 kilocalorie per mole. This much amount of the energy, or we can call it as a van der Waals strain here. This is a van der Waals strain, 0.9 kilocalorie per mole. Now instead of N-butane Gauche interaction, here the 1,3 diaxial CH3H interaction is there. And this 1,3 diaxial interaction, it also produce 0.9 kilocalorie per mole. This much amount of the energy associated with the 1,3 diaxial CH3H interaction. Now how do you see that? How do you identify, or how do you recognize that 1,3 diaxial interaction? Now look at carefully. Once you understood this, it's very easy to find out the relative stability of those conformations. Now look at here. One methyl group which is at axial position 1, 2 and 3. At 3 position there will be a hydrogen atom which is at axial position 1, 2, 3. Here is also as a one hydrogen atom which is at axial position. When they are coming at this position, they generate the 1,3 diaxial interaction. Now count how many 1,3 diaxial interactions are there. Suppose let us look at the second one. This is one of only axial bond produce the 1,3 diaxial interaction. Equatorial bond do not produce the 1,3 CH3H interaction. 1,3 diaxial interaction. Diaxial. Look at here. Di means 2. Axial means what? Axial bond only produce the 1,3 type of the interaction. That's why it is called as a 1,3. And equatorial do not produce the diaxial, that type of the interactions are. Now look at here, 1, 2, 3. Here is a hydrogen atom. Look at here, 1, 2, 3. There is a hydrogen atom. They create the lot of steric interaction, 1,3 diaxial interaction. Here also 1, 2, 3. At this there is a hydrogen atom. 1, 2, 3. What is that here? Axial position. 1, 1 2 3. Here is a hydrogen atom, they generate as a hydrogen bomb. Now here this is at axial position, count this side and count this side, 1 2 3. So here is a one of the hydrogen atom, they produce the 1 3 diaxial interaction, 1 2 3, they can produce as a one hydrogen atom over here. So similarly now 2 1 3 diaxial interactions are there, and therefore how much energy, total energy 2 1 3 diaxial interactions are there. So 2 1 3 diaxial interaction, 2 into 0.9 is equal to 1.8 kilocalorie per mole. This much amount of the energy associated with this 1 3 diaxial interaction. But in addition to this, there is the observed value of this is now is a 2.7, right? And there is a N-butane Gauche interactions is there. N-butane Gauche interaction 1 into 0.9, total become as a 2.7 kilocalorie per mole. Sorry, here 0.9 means just I am correcting here, 0.9 is equal to 0.9. So total energy associated with is a 2.7 kilocalorie per mole. This much amount of the energy associated with this means this conformation has 2.7 kilocalorie per mole. This also has having as a 2.7. This also having as a 2.7. Now how do you calculate as a N? How do you recognize N-butane Gauche interaction? Look at this methyl group and this methyl group, they are creating as a 60 degree, means Gauche interactions are there, and Gauche interaction produce the 0.9 kilocalorie per mole. This much amount of the internal energy is associated, and therefore it's showing as a 2.7 kilocalorie per mole. Now let us see here, look here. As we know that the Newman projection formula, do you remember that Newman projection? There are the 4 conventional ways to represent the organic molecule on the blackboard to understand its physical properties as well as chemical properties, to understand the 3D structure. So look at here, look means see, or look at here. Here what do you see? Newman projection formula, as we know that all the rules for drawing as a Newman projection formula. Let me clean the board first here. Now I am trying to calculate how this 2.7 kilocalorie per mole. Now look at here, as we know that this is a one dot here and it having as a one circle. You can put as a one dot here and circle. Remember, this is a carbon number, this you can call it as a carbon number 2, and this circle is a nothing but as a carbon number 1. Remember, imagine this one. And now this is a carbon number 4, and this one you can call it as a carbon number 5. Now carbon number 2 and carbon number 4, which is 2 and 4, which is joined by one group at, there you can call it as a 3. 1, there is a one hydrogen atom and there is a another hydrogen atom we can put here. And now at 2 position there is a one methyl group is here. Methyl group you can draw like this. Here methyl group, and here there is a hydrogen atom which is at axial position. At 4 there is a 2 hydrogen, and these 2 hydrogen we can draw like this. And now 5 has one hydrogen axial here and one at equatorial, and this point joined with the 6 with that one carbon atom. You can show like this. One here one of the hydrogen atom, another bond should be here. This is a carbon number 6. Now here carbon number 1 methyl group is here, one methyl group is here. Now if you measure the bond between this methyl group and this methyl group is a 60 degree, and that conformation is known as a Gauche conformation, and Gauche conformation has 0.9 kilocalorie per mole. This much amount of the energy associated with this, and therefore this conformation total energy is associated with the 2.7 kilocalorie per mole. In this way we can easily determine, or we can easily measure the relative stability. And now tomorrow's lecture we will start the trans 1 to EE or AA form. I think with this let us stop today here. Remaining we will see the next time. Have a nice day. Thank you.